As always, if you've been here before, for my case, I'm not. This is going to be very informal. We'll go in lots of different directions, just have lots of questions. I'm slightly confused as to what we're trying to do here. So we're probably going to do too much or too little or the wrong thing. So some of you may have come to a talk on databases last week here, last Wednesday week ago, with John Daniels and Bess Lansberg, which was kind of really just talking about SQL, and before that was actually spent an hour up to 2 hours talking about schema and building databases and best practices for databases and so forth. I'm going to try to gloss. We can talk about building databases. We can talk about database design and all sorts of interesting things, but I suggest we don't, unless enough people want to. Primarily because, in my experience, most people actually end up just being forced to use the database, and it is given to them, and they have no authority to actually control how it's being built or designed, and they just take it the way it is. However, there is no reason why you can't build your own databases. In many cases, it's quite simple and pretty straightforward. Although it can get very complicated, just like all software engineering. You want to think about the future and do all sorts of good things. So it's a whole course on its own right, and it's also, most people get away with it in 10 minutes. Okay, there are several databases that will actually just infer your schema for you based on the data you give it, and it may or may not be correct. There are tricks to making it go faster by indexing and so forth, but that's all. We can talk about that if you want. And the other thing we can talk about is just talking about SQL. How many of you are here because you want to learn the basics of SQL? About half, okay, which is fine. Okay, moving on. Okay, so that's fine, because so we'll talk about the basics of SQL, and then we'll also talk about SQL in R. So that's 3 different things, okay? Obviously, the basics of SQL, and do them in R, but we should actually just focus on R. And when I say R, it's really any client you want. This is, in some regards, super high level and simple. I actually was writing these slides because I know how to prepare them. May not always be good. But there's nothing here. SQL is incredibly simple, and pulling it in from R is not particularly complicated either, which is good news. But it also means that. So, tell me what you want to know as we go along. Okay, as always, it's just like this is an interactive discussion. Okay, I put up these slides. I pushed them all, I believe, to here. If that's not true,
I get an error saying the page it's not the page you're looking for.
Yeah. Say me too. Hang on a second. So that's easy to do. That's the SQL workshop. That's why. 1 second, because thank you. Good thing we talked about this. SQL workshop. So that's the link you want. SQL workshop. I'll go back over here. Git add slides. Git commit. And now, having found them, you should be able to find them. There we go. No description, no nothing. Okay, minimal. Okay. So you can play along. There are. I was starting to put together some data. I have lots of data sets, and when you're trying to teach this stuff, you want to go for minimal data sets. I always try to create something slightly more interesting, and then I sort of ran out of time. But there's a very small data set underneath here in one of the subdirectories, which we'll look at, which is really nice because you can actually look at the 2 tables and reason about absolutely everything. Do it in your head and then check that you got the right answer. And there's also another database. There's also another directory under there where it has the R code to generate a very large table, like in the arbitrary millions of records, which can be interesting. So people want to talk about the basics of SQL. We will talk about those. We will talk about in R as well. And I'll also just go through I'll also go through what a database is, just to clarify everything. Just again, if I'm going too slowly, let me know. If I'm going too fast, let me know. Now here, this is what I was thinking about first. Okay, just to thank you. I don't want you to. It wants to talk to my phone. Go away. Okay, we have a data set like this, 3 columns. ID, okay, so we have student ID or employee ID or whatever, age and sex, okay? I'm just showing you the first 2 rows, okay? If not, you can do this in your head. Okay? How would you compute the mean? So this has got, let's say, 100 observations. So I'm hoping that you would all know how to compute the mean here and the median, that you would read .csv into R or Python or whatever it is. I really don't care. Okay, come on. And I hope you all know how you compute the median. Okay, function in R called median. And if you compute the mean by sex, how would you do this? How would you compute the mean age by sex? T-apply. Okay, it's a group by operation. If you want to T-apply or by or an aggregate, you're just going to, or you can just split this. You split the records by, you split the age values by sex. You've got 2 subsets, and then you do, and then you apply a function to each, which is the mean. Really straightforward and simple. This is what we do in statistics. I've been talking to my class. Which, every time I talk about this stuff, what do we do in statistics? We split stuff up based on 1 variable or 2 variables or more. We see if the relationships are the same, the distributions of the relationships are the same. If they are, we put them back together again. There's no effect of that characteristic. If they're different, we now actually have an interesting characteristic. We put it into regressions or not, but we slice and dice, put things back together again, okay, depending on whether they're similar. So this is all very simple. It's got nothing to do with databases, okay, apparently. What if I have 500 million observations? How would you go about doing this? I told you we had 100, and now I'm telling you we have 500 million observations. Each of them is 3, okay, exactly the same structure. How would you do this? How would you compute the mean? Sample? Ooh, wow, okay. How would you sample a CSV file?
Choose a random number of rows to read in.
So you're going to have to visit every row, though. You're going to have to walk through and check if it's in your sample. So you're still going to have to actually process every row. And if you do this in R, you'll be there for a long time. Because either you're going to have to suck the entire 500 million, not, by the way, take any, 500 million was when I stopped typing. Okay, I can add zeros here, okay? So you would have to read in all of the lines, okay, and after an hour and a half of it reading the lines in, you take a sample of size 10, and so you throw away all but 10 observations. You may saturate the memory limit here. So another way to do it is just to loop. So you could, if you knew the number, if I tell you how many lines there are, you could just do a random sample of 1 through n, when you take out 10 observations or however many you think is good. Okay, and then you could loop. Basically, you order them. So it's I would end up with, let's say, we take a sample from 1 to 500 million. We end up with 4739, the first number, 201, 373, and okay, and so forth. What I'm going to do is I'm going to order these, and then I'm going to read through 201 lines, pull out that value, keep it, and then move on to the 373rd line. Okay, so doing a skip. So you're doing this in R. It's very slow because you're looping in R. So this is not going to be good, but we save a lot of memory. But it's really slow. So any other approaches? I'll give you a hint. We're talking databases. Okay, so the problem is sampling in R is not actually that easy. We either have to sample the entire collection of elements, which means we have to suck them all in. They're too big to suck in, and I'll just make it bigger and bigger. Or we have to actually loop to sample, so we write that in C code, and it's much faster. We can't do it in parallel. It's slightly annoying, and so forth. And also, Nobody said, you can't sample. Or how many rows should I sample?
No.
More than enough. A little bit more than enough. Yeah, so depending on the question, it depends on how accurate I have to be. I mean, so I actually need to do some, I need to know what the standard deviation, if I knew what the standard deviation was, I'd probably computed the mean along the same time. So we kind of got a problem is if we don't know anything about this, we don't actually know how big the sample size should be to actually get the power and the accuracy that we care about. So, and a lot of people are really funny. They have a database of a whole lot of samples, 500 million samples, and they want to actually get the precise answer, even though this is a sample. So you go like, hang on, why do you give up on statistics when you actually come to deterministic operations? So sampling is a great idea, but even then we have problems. So there's some conceptual issues. One of the things you might do is, well, first of all, you get on a big machine with lots of RAM. Okay, so you take it away from your laptop and you get onto a bigger machine. And we have bigger machines which are for production services. Okay, so they're shared machines, or they are shared, but they may actually have a lot more RAM. So this is good. And oftentimes those servers actually are used to run services that people can connect up to. Okay, and that might be a database. So one of the ways to think about this is a database. Let me just go back and say, so a database will be able to compute the mean. I hope not all databases will get it right, but they think they know how to do the math. They don't, because they think if you just add up all the numbers. There is a trick to this that you have to add them up in the right order, okay, or you have to do some numerical adjustments. They know how to do group bys. How many of you know about medians in databases? Most of you don't, because they don't do them. They're just, you have to sort them. So, and databases like to go one record at a time. That's the trick with them, is they don't keep everything in memory. That's the beautiful thing about the difference between R, is that they just don't want to have large blocks of data in memory at any one time. They want to be able to cleverly traverse this in parallel, do all sorts of interesting tricks. And they're very, very clever, but they don't know how to do the median. They will do the median, but they will explode and they will get very unhappy. So we've got a problem here with the median. So we haven't quite solved our problem with the database, but it's worth a shot. Okay, so speed is an issue. So even if you're not stuck using a database where your data is given to you as a database, and all you want to do, and I find that a lot of people want to do this, the data are in a database. Your PI or your boss says, "Go get the data." You go, "Great." What you do is you basically suck it immediately out of the database into a CSV file, and you just say, "That's it. I have no interest in SQL anymore." There is a time when you are interested in SQL, when it actually will do things much more efficiently for you, because it's on a big, fast machine and you're on a very small, underpowered machine, or because you want to keep going back and getting dynamic data, okay, where you actually have to get the correct data. Okay, so those are the two primary motivations. But to a large extent, for people who are not in industry, a lot of people just want to get the data out and take a snapshot and then never go back to the database until they have to actually update their data themselves. Whereas in industry, all the customers are coming in and their records are being updated in milliseconds. Okay, and you need to be able to be doing things in real time, potentially. Okay, what is a database? A database it's very simple, but there's people talk about database engines and database servers and databases and tables and all these things and they confuse the concept of a database engine or a server and the database itself. A database server is a piece of software that is running and actually has multiple databases inside it. Okay, so a database server or engine has potentially multiple databases. Each database is a collection of tables, related tables, okay? Tables that are totally unrelated to each other are typically in different databases, okay? But they may still be served by the same machine, with the same user account, and also so forth, okay? And what's a database? It's a collection of tables. The tables are analogous to data frames. This is SQL in R, so I'm going to use analogies to R. You know, they're just tables. They're rows and columns. This is where what we've been living off since the late 60s, okay? A table is just a collection of columns, their frames, their columns and rows. Interestingly, before we actually create a table, in most cases, we have to tell it what the types are. and they all have to have exactly the same type, and they are of limited types. You can stick anything into a cell in the database. You can stick an image into a database. You can stick an R data frame into an image or into a cell in a database. But what it is generic. It's just binary data. Nobody knows what it is until you pull it out and actually operate on it. But you can actually stick anything into a cell in a database. So we basically have rows and columns, okay? And we specify what the structure of each record is, okay? So we talk about a database, collection of tables. Each table has columns, and the rows are called records. We just use different terminologies than we do in data statistics, but they're all trivial. If it's confusing at all, yeah, okay? I'll start interchanging the two, okay? So we have a schema, so you have to specify the type, and you can actually put constraints on the types, like this must be positive, okay? And this must be one of these three values. It can't be an arbitrary string. R doesn't quite do that. Python doesn't quite, because CSV files don't have that capacity. But here we can actually put constraints. We're saying we're declaring things ahead of time. The most important thing is we have a bunch of tables. Okay, let me see if here is an example. Okay, let me pull it up here. Okay, this is slightly bigger. This is a description of part of a database. Okay, so it starts becoming a little complicated, okay, a little unwieldy. And there's good reason for this. What this is the IMDb, the Internet Movie Database, okay? This is one representation of it. It comes in various forms, and we put it into a database that looks approximately like this. We added some other stuff, okay? So this is the title of the movie. It has, each movie has an ID, okay, to uniquely identify it. And everything about that movie corresponds to that ID. Okay, so you have a movie keywords, we have the movie link, we have all these different things. It's actually a little hard to look at these schema. You actually have to sit down and truly understand what's going on. Imagine you had all of these different CSV files on your hard drive in this folder. You'd actually have to understand what the relationships are between them. It is tricky. And the reason, why do we do this? Why don't we just have one huge table with columns where basically each record or each row would be a movie, and we would actually have something like the title, okay, the year, okay, so there's the year, there's the year it was produced, the year it was released, the revenue it had, okay, the actors in it would be what? Do we want to put the actors in? So we'd have actors that would go, you know, lead actor, second lead actor, third lead actor. Oh shoot. Okay. So we just have lead actor, and then we have supporting actor, supporting actress, so forth. What about if we have two of those? We're in trouble. Okay. And if we want to have the entire cast, we'd actually have to have an arbitrary number of columns, most of which could be empty. So when you get to there's one movie that will have 500 people in the cast, we would have to have a column for all 500. And most movies would only use 3 or 10 or 15 of them. So most of them would be having garbage in them, just useless values to take up a huge amount of space. And then somebody comes along and publishes, or somebody releases a new movie that has 501, and our database is now screwed. We actually have to add an extra column, and that's really not pleasant. Okay, so this would be a very bad way to represent it. So how would we represent it better? Put the actors in a table. We could do that. I hate tables. I hate different tables because then I have to connect the dots, don't I? I basically would have to. I would actually have to have something over here that would sort of say. I would have to have. Here's my actors. I would have to have actors. So it's just worthwhile thinking about why we do this, and then what the consequences to this are. We would have actors over here. Okay, so we got actor number. Okay, so this would be the person's name, first name, last name. That's not going to do it because some people have the same first and last name, but you wouldn't uniquely identify them. Okay, so we could have that, and then we have Joe Smith. So we're going to actually have to give them a unique ID here. So the first Joe Smith gets 275,001. Joe Smith gets 961,000. The next ID when we actually find them. So we have a unique ID here, but we wouldn't have their first and last name. their year of birth, maybe, or something like that. So how do we connect them to the movies? So we have a movie over here, which is, here's our movie, and everything's got a unique ID because there are movies with the same names, even though they have totally different, they're just remakes of the same thing, and so forth. So the ID, the title, the year of release, and so revenue, or whatever it is. Okay, well, hang on a second, the revenue is not the total revenue, it's the revenue by year or something like that, or revenue even by location. Domestic and global, so and then by year, so we may actually want to repeat that, because otherwise we have to keep adding a column for each year, so this is a mess. But then how do we put the actor in?
Well, there should be a column, right, that connects all the different tables within the database.
That's what we're going to have to actually do, so we're going to have to put the actor in, so we actually have to repeat all of this multiple times, one for each actor, and then point over to the actor ID, which means we're going to repeat all this, which means we've got replication again. And then some idiot comes along and goes, by the way, that you got the title wrong. It actually has an apostrophe in the S and not, and that's missing. We have to repeat, we have to fix it in every single place. So there's a lot of redundancy in here, which we can't have for very large amounts of data, okay? Whereas if we actually keep things out, we've avoided the redundancy with a lot of columns, okay? And a lot of, and not being flexible to extend. Here we actually have repeated a bunch of things, which is also redundant. We don't care about. Okay, so we want to avoid that. So we can just basically say, okay, there's another table here that actually links all of the actor IDs to the movie IDs, and that allows the same actor to be in multiple movies. So we have movie IDs, actor IDs, and that's going to be a very, very long table, but there's almost no information in it. And when the person changes their name for some good reason, we just go and change it in their information, not in all of the rows where they occur. So we're avoiding redundancy, and because it's only things are only in one place. What is this? Okay, so because it's not in because it's only in one place. Okay. Life is much better, but it makes it much more complicated to work with. Okay, a single table where we can just go get the columns and we can do subsetting on these things is much easier. What we have, so we can get away, we can do this in R with one single table, which is wide format or long format. The long format is much more preferable. That's all. The wide format is, okay, we have 500 actors, most of which will be empty. When we get the 501st actor, we're in trouble. Okay, the long format is that we actually sort of we repeat, so there we would be repeating the movie information, but we could at least get the actor ID. We could put the actor names in, but we'd have to end up repeating a lot of information, so that's good, okay? But over here, with these multiple tables, even with just two tables, we're going to do a lot of what you may not see because there are functions to hide this. You're going to do a lot of matching, okay? This is the heart of everything. Match the keys in one table to the column in another table and say that this row corresponds to these 3 rows down here. This next row corresponds to 5 rows in this table. And this one corresponds to nothing in this table. Okay? So you had a question, sorry.
Well, when you were talking about this new idea of the table, would there still be the 500 IDs of the movie ID with 500 different actor IDs? Or you still have 500 rows in that long format?
If we had 500, because we had 500 actors. Okay, sorry, just to go. So if we had 5, so in the movie, so I'm just, and we can. This is where good schema design is hard. You have to think about what you're trying to do and how to leave it open. If we so this would be the movie ID, and this would be the actor ID. So this would be movie 1 had only 2 actors, and it would be actor number 201, and the same movie would have actor number 307. And then our 500, our other movie is actually number 2, which had 500, and it would be 500 actors in here. Okay, and then these guys would shoot off to the actor table, which would be actor. This would be actor, and we have an ID, and then we have a name, and then the year of birth, and so forth. Okay, and then, so we could look, so this would give us this. So here we can actually see how we have the same actor might be in multiple movies, and we'd be able to see that. okay, off of this. And then we'd be able to go back and ask, what's that person's name? Okay? And again, what we're going to do is, we have 307 here. We sort of say, okay, go find me the actor who corresponds to these two things and give me their names as 2 rows in a new table, okay, to actually that I actually want to see. Okay, does that make sense? Everyone happy? And if this isn't clear, just yell. This is the heart of databases. Okay, it's separating it out into these hideous numbers of tables.
Do they ever organize that more as like a nested list? So just basically have 1 row for each movie idea, but then within that row there's basically another
Vector.
list or another vector.
So the answer is almost never. Okay, so I was debating whether I would actually start by talking about this just to see if I can see how many people left. Yeah, but you're basically saying we could actually just have, we could have movie number 1 and we could just have 201, 307.
Yeah.
Okay, and then we have number 2, and then we have 500. The trouble with that is, well, how would we represent this? This would have to be a string, or would have to be some sort of data structure. It could be a vector. There's no reason we can't do it. We could actually put this in as a vector. Okay. Okay. Or we can make it a string. But now, if I want to find out is this person in this movie, or okay, I have to go through and break up that string and start doing some string manipulation. We could put it in as a vector. But unfortunately, SQL does not have vectors, but it can handle vectors, as I said. But what they go in as binary objects, okay, or blobs. Literally, they're called blobs, which is kind of just, and that's exactly what they are. They look like blobs. It doesn't understand what they are. It can't look into them. It just says, I can hold the lights around and give it back to you, but I cannot interpret them unless you provide me a lot more code, which we'll talk about much later on. So that wouldn't be very good. No, what we actually want is, we want to have things being integers, reals. We want them to be characters, okay? In SQL, we call them varchars, variable characters, so that sometimes we actually know they must have exactly five characters. In other cases, we say we don't know how many there are. That's a different deal. Okay, so we want these guys, and we don't want a lot more. We actually do have different types of integers, 4-byte integers, 8-byte integers, 2-byte integers, and so forth. We have different ways of doing this. But there's a reason why we restrict ourselves to these. There's a reason why we want tables, rows and columns. And it's very nice because what it is, so you may have come across this, relational database management systems. We also call it a relational algebra. Who knows what an algebra is? I knew we'd get them out. But the nice thing about an algebra is those of you who sort of did group theory or field theory, okay, basically it's got, okay, it's a set, and all the operations that it has on it actually keep the elements in the same set. So we're always getting tables back, and we always have the nice relationships between them. So there's a nice theory about this. This was developed back in the 70s. Okay, and it says, look, if you do it this way, we can reason about this really nicely, and everything is clean. Whereas if you do it this way, we don't know what's there. The operators won't work, and bad things happen. Okay, so it's just not as elegant, as clean a solution. We end up writing a bunch of horrible code for special cases and so forth. It's not nice and clean and extensible. That's the beauty of relational databases. It's a clean, functional system that is very simple, too simple. There are a whole lot of other types of databases, object-oriented databases, and XML databases, and NoSQL databases that you can do, that people do all sorts of interesting things, but for very different purposes. This, we need them to be in this hideous long form, okay? It's basically the rule of thumb, okay? Everyone happy? So we will get to this near the end, or whatever. I hope, how many of you use the match function? Okay, it's really useful to understand what the match function does. I know that the dplyr and other things have left joins and right joins and stuff. I find it really important to actually go through the mechanics of actually understanding, because it's very short. It's 3 or 4 or 5 lines of code at most, and then it's like, that's what's going on in the database. Thank God it's doing it for me at immense speed, and it's actually taking a bunch of shortcuts to actually make things very smart, okay? But that's what's going on here. So you could imagine just sucking all these tables in and actually doing this in R, but even then they start getting big, and you have to do a lot of work. Okay? So, again, a big part of this is that we want to avoid memory buildup in R, because that's what R does for a living, build up memory. Okay? And client-server model, okay? We're going to actually get away from this to some extent because it's easier, but most databases are organized as client servers, okay? So things like Postgres, MySQL, Oracle, Teradata, all of these things. There's so many different databases in the world, and there's a reason for this. The data is stored on a central machine, so there's one big data warehouse, or there's one big, let's say, machine that isn't a laptop that's running 24/7. That is getting all the transactions from all the customer data or all the electronic health records and so forth. Okay, that has to be a robust machine that is never down, okay? But the clients are coming in and connecting to it. There's doctors getting this stuff as they start up and down. It's not quite, they don't have the same reliability issues with their client software, but they need to be able to get to up to the minute, up to the second accurate data, okay? So some people are uploading data to the database, other people are just pulling it down. So you've got two different types of clients. Sometimes a client will do both, update stuff and download stuff, but they need to see the current view. And for that to happen, we can't just sort of pull it down at the beginning of every day. We need the current version. So the client has to, and we also do not want to pull down all 250 terabytes of data. And then every morning pull down any changes to this. We want to pull down just the bit we're interested in, and even just the bit we're allowed to see. We're not allowed to see all the data, okay? So we actually want a broker. We want somebody who's actually managing access to the data, who's managing incoming data, outgoing data for different people, and that's actually a service, okay? And that's good. It's a live database that has transactions. And the word transaction in database world is really important. It says when I start sticking stuff into the database, so I'm gonna add 10 rows. If any of it fails, I want the whole thing to fail. Okay, we must have an integrity in the system. We cannot end up with a corrupted system. Okay, where the data may be partially correct in one table, but not in another table, and as a result, the data could be erroneous. So there's a lot of stuff built into here to make sure that when a transaction is started, it either completes or it gets rolled back. Okay, and this is a very big issue. The other big issue is that this thing has to be as secure as they come. Okay, apparently not. Okay, apparently you could. Apparently we aspire to this in certain cases, but there are rules and regulations, and we have to implement a lot of security on these things. Okay? Oftentimes the server is running on one machine, the clients are running on another machine. I'm on my laptop, whereas the server is running on a massive machine that can actually handle multiple terabytes of data. Okay, that has lots of CPUs. Okay, and life is good. The client's running elsewhere, sometimes on the same machine. Okay, on this machine later on, you'll see I'm running a server and my client on the same machine, but there's no reason why we can't be on separate machines, except for security and network access and all that sort of stuff. Okay, so basically we're always seeing the current contents of the data. Okay, we suck something down, we can choose to walk away and just look at that, but we can always go back and be looking at live data. Okay, so we can make the same request at a different time. We likely to see more or less data, or more specifically, different data. Okay? Okay, and they can run on the same machine, but oftentimes they don't, and oftentimes you wouldn't be let near the machine that they're running on. The system administrator would not even let you in the building of the machine. Okay, so when that happens, we're in a totally different world. Okay? Okay, administered centrally with typically grumpy people.
I was going to say literally. I mean, there are building.
In some places. Yeah. He used to work in the military. They had a lot of armed guards. But yeah, so some things are really, really important and they're really, really secure. You can't get network access to them. And other times you can, but and different things. And sometimes we'll make copies of them, but they're not. Then they're separated from. They're not live. Okay. In many cases, you will have to log into a database. And that's not logging into the machine, not SSHing to the machine and starting to talk to it. It's actually logging into the database. So you may have a totally different user ID. You may have totally different passwords for that, for the database, which is important, but most important, you may not have access to certain pieces of the database, even though you have access to the entire machine. Okay, so it's a good idea to keep these two separate. Okay, that you have a login on the database and a login on the machine are totally different things. Okay, but unfortunately, this is a real problem. Is people actually have to administer permission. If you want to get access to a database, you have to apply, get login. It doesn't just happen instantaneously, which is annoying because if you want to actually do something right here and right now, I just want to do it. Well, first of all, if you do this, I'll show you how to do it. I actually went through the process, and it's very simple, but it's not quite so simple, but it's not too bad. You can set up your own client server, okay, on your own machine and actually run through this, and you don't need to be root to do this. You can do this in your own user account on any machine. It's not a big deal, okay, but it's also kind of handy to be able to do it without a client server because it just makes life slightly simpler. The client, okay, again, people get confused about this. This is one of the reasons I'm just mentioning, just want to belabor this. The client runs on each individual user's machine, not the database administrator's machine. Okay, it does not run necessarily on the database machine. Okay, that means that all the software has to be installed on multiple clients. Okay, just because the system administrator installed the database server on a machine doesn't mean that you have no software to install. And it's actually different software that you have to install because the server is one piece of software. The client is another related but different piece of software. Okay, okay, so they have to be installed separately. Okay, if you're not running the server, just install the client. And if you're only running the server, don't install the client. Actually, do install the client because you want to test. You want to test that the server works. Okay, but for the most part, these two things are very separate. So if you're using Linux or Homebrew or something like that, you have to decide which package to use, the client or the server, or both. But you actually want to get you don't need both. Okay. We also have these wonderful things. Life is getting fun these days, okay, where we actually have these distributed databases. So it's not that, so the client is on one machine, the server's on another machine. We have distributed computing. But in many cases nowadays, the data are too big and the number of users, the number of clients is too large. What we actually have is the server is actually running on multiple machines. Just like Akamai and Google, basically you make a query and you go there. You go there, okay, and it's distributing, it's load balancing to get all the requests handled in sort of simultaneously without waiting for one to complete and then serving the next guy. We want to do this in parallel with very little latency. So what we actually do, so you can do this in various ways. One of them is to actually just break the database up into multiple copies, and then everyone has access to the same thing. So your requests can go anywhere as long as they're just balanced. Or alternatively, what you can do is you can basically divide them up into disjoint elements, okay? And then all the queries, somebody looks at the query and says, he knows how to do that. Another query, she knows how to do that, and it distributes it out. We do this thing called sharding or shared nothing. Okay, so there's different theories, different design, different versions of this. Life is great. Okay, if you're getting into distributed databases, a lot of fun, but it's very technical and performance is critical, and consistency is critical. So it's a seriously sort of complicated thing. Here, I don't know how many of you know about SQL Lite. How many of you use SQL Lite? Everybody put your hand up. You all use SQL Lite, okay? Because if you're running a web browser, if you're running OS X or something like it, we all use it, okay? Because everybody needs a database, okay? Because lots of different pieces of software need databases. They need to store so a web browser gets your cookies. As you visit sites, it gets cookies and has to store them so that when it comes back, like when you quit and come back in to your browser, it still has them there, and it needs to be able to look these up very quickly. It needs to cache a lot of stuff. Where you visited a page, it holds that around, checks the time, has certain characteristics. You can imagine tables that store this stuff. The cookies apply to a host, their website, not individual pages necessarily. So we have to look these up very quickly. So everybody's using this stuff. So you need a client server. Where does the server live? Sometimes it might live on Google, where you're going back to Google and reporting all your web browsing history. Okay, not so good. Okay, so we like to keep it locally, but then we don't want to set up a client server. So people have developed this thing, which is SQL Lite free, which is a very simple version of SQL Server, okay, or of a database server that doesn't have a server. All it does is it says, all these tables live in a single file, one big massive file, and that is a database. We might have another database in the same directory, which has a different set of tables, and then we can access those two databases as if they are just local files, and we'll treat them as a server, but we don't actually have to have permissions. We don't have to have logins. We don't have to have any of the complexity and network access that we had with a client server. Okay, so this is a whole different ballgame, and boy, does it make teaching easy, because now anyone can actually just run this locally on their own machine with no setup. Okay, and that's the beauty. So there's no, so there are, so in SQL Lite 3, there's no server client model. It's just a database which we create using some tools, either R, Python, or its own little tool. Okay, each database is a separate file, and then basically Python, R, and its own tool and anything else can actually just access that file and start querying tables. How are we going to do it? We're going to do it through SQL. Okay, but now it's a heck of a lot simpler. So this has got nothing. So we've just spoken at length about what the structure is for databases and why we have the tables. The way we have the tables, we talked about the client-server model and all that sort of stuff, and now we can assume all this away. If you're lucky enough to have somebody else set up the database and they gave you a login, all you need is the login and the password. Hopefully they need a password. Okay, not always. Okay, and then you can connect to the database and you can start making queries to it. You can start asking about the tables and combining the tables. So that's what SQL does. If you don't have access to a database that's already there, you can set one up with SQL Lite 3. If you go to the Git repository, and if you go down into the data example, data EG / presidential orders, there's a file called CO there for customers and orders. CO, that is an SQL Lite database. If you clone that or just download that, you can start talking to it immediately. Okay. For example, I can just go off and do this, which is data EG presidential. Okay. So there's the name of the file. There's CO. There. It's just a simple little file there. As with everything, let's look at file of CO. What is it? It says I'm an SQL Lite 3.x database. It was last written using this version of SQL. Who cares? Okay, thank you very much. We might care because if we got a totally different version of SQL, they may be incompatible. But if I just do this, SQL Lite 3, if you're having an OS X, if you're running OS X, just try that in your terminal. It should be there. Okay. If I just do CO, it says, sure, there we go. I am now talking to the database. And just to show you, now this is not an SQL command. Oh, welcome to the joy of non-standard SQL. Okay, but basically it says this. I'm attaching to this database. I'm connecting to this database. Same thing as logging in remotely to some machine and saying I want to get access to the CO database. And it says I have two tables. Okay, and I can look and find out what those tables are. I'll even actually just show you. This is a really simple. Okay, that is the schema. This is the description of the columns. And if you actually look carefully, there's a command that isn't just a description of the columns, it's a description to create the table. This is an SQL command, okay? Okay, and this is the beautiful thing is SQL tends to be implemented in SQL because we only need a certain set of parameters. But the customer ID is an integer. The first name is a variable character length. Okay, it's a string. The last name was string. The email, we have an email address, we have an address, city, street address, city, zip code. Okay, these are all strings. The states are just two characters. This could be different. Okay, so anyway, we're now talking to a database. And by the way, just for fun, I'll just show you what these look like. Customer. That is the table. It's a little bit too wide. Okay. This is the table. There's the customer ID. There's the column. There's the first name. There's the last name. These are the fields. These are the columns. Okay, here are the records. Okay, and off we go. Okay, okay, that's what it is. And again, stuff we'll talk about later on. By the way, what am I typing here? Okay, I got the name wrong because I named one of them customer and the other one orders. Put an S on it just for fun. So I'm sitting in here in this weird shell, okay? I'm running an actual terminal, and then in the terminal I run SQL Lite and I got a prompt. Just like R gives you a prompt saying I'm R, and I'm talking a weird language to this, okay? It's not the shell, it's not R, it's not Python. It is a weird form, a weird dialect, but this is a general dialect of SQL. This is the SQL command, okay? We're done, okay? And actually, that's all you need, okay? Is just give me all the rows from customer. That's all we're talking about here. Make sense? Everything is built off of the select command, okay? So, where are we? Okay. One of the things you can do if you want, and we can do this if you'd like, there's a thing called DB browser. If this makes life easier to get started, use it. There is a graphical interface for most SQL databases. Okay, so this one is for SQL Lite 3. You just point it at the file, and just now instead of what we did through the terminal and making commands and saying show me the tables and show me the schema. Okay, and we can run this if you want. If anyone wants, I can run it and show you. But this basically is now, this is running on the IMDb data. Sorry, this is on customer data. Okay, this just shows me the schema for these things. Then I can click over here. I can go over and say hello. Okay, I can select execute SQL. I can say select star from orders, and it will show me the results down here. Okay, I can also look at them in the data. I can start playing around. This is great, isn't it? This makes life easier. Everyone loves graphical interfaces, except me, apparently. Okay? This is great, except for, how do I make a plot? I rarely want the data, and then, yeah, I'm done. I got the data, and then, okay. It does have a mechanism by which we can actually export it to CSV in Excel. So, okay, so if your goal is to get the data for your boss and give it to them and go home, you're done. Okay, this is a great tool. If your boss says, draw me a plot, and then you go, dang, okay, do I need to use the data or can I just draw you a plot? Okay, so this is not an ideal workflow. This is a great way to explore and it is really a very useful way to explore databases and play around. Start smacking SQL statements in here and hopefully they give you good error messages. Probably better than R and Python because they have extra information here. But it's like RStudio, but it's not as powerful as a workflow. Okay, so you can't really do that much with it. Okay, but we do dump it to CSV and Excel. That life is great. An alternative to GUI browsers is where the databases date back so far there were no GUIs. Okay, it was like dumb terminals and those stuff. So we will always be doing this. We basically want to get everything into R, Excel, or Python, whatever it is. And there is a mechanism from Excel to actually connect to various different databases. That's a pain to set up, but once it's set up it's easy to use, and you can actually populate entire spreadsheets, multiple sheets with data from a database, and it can be live. It can go back and actually update itself as you reopen it. Yep.
Could you explain the difference between SQL Lite and is it DB browser?
SQL Lite is many things. SQL Lite is a piece of software, okay? And this is very confusing. It's like databases and database management systems where a server handles multiple databases. SQL Lite is a piece of software which has multiple components, okay? One of them is an executable, a command line tool called SQL Lite 3 that you get, and you point it to a database, a file, and it can start talking to that database. SQL Lite, the software system, also has a library. Okay, Lite SQL Lite 3, which is the engine, which is all the brains of actually being able to talk to those files. So SQL Lite 3 uses Lite SQL Lite to provide a command line tool, okay? And the DD browser is another thing, analogous to SQL Lite 3. It uses Live SQL Lite to provide a graphical interface to the same Live SQL Lite routines, and all of the smarts is built into Live SQL Lite. okay, to talk to the database. And that means to be able to query the database and also to inject things into the database and add new tables and so forth. So SQL Lite 3, the command line tool, and DD Browser are clients that use Live SQL Lite to talk to essentially the database itself. Okay, make sense?
Yeah, so it's essentially the same thing, it's just that the DB browser provides a interface to work with.
SQL Lite 3 provides a beautiful interface to work with.
Well, it's
It's all in the eye of the beholder. Yes, DD Browser provides a nice graphical interface for pointing and clicking and easy use until it stops doing what you want it to do. In fact, actually, SQL Lite 3 doesn't do very much either. It's more of a exploration tool. The trouble is we actually want to get stuff into R or Python and then go on and do something with it as if the data had come from a CSV file or something like that. So we want a different workflow. But yeah, those two, SQL Lite 3, the command line, and the DD Browser are just front ends, or interfaces to the functionality that is in Live SQL Lite. Okay, well, that's the heart of things. And what we actually do is we connect to Live SQL Lite in R and in Python and all these other tools. We go straight, so we just provide a different tool, a different interface, a different set of functions to access the functionality in Live SQL Lite. Okay, that makes sense? Hope that's more detail than you absolutely need, but it's actually, I think it's helpful to sort of say what's going on. If we were to do Postgres, and I'll show you Postgres later on. If we were to do Postgres, I would be connecting to Live Postgres, just for fun. So here is Postgres running on my machine. I'm going to connect to it through PSQL, okay, which is just like SQL Lite 3. This time it asked me for a password. Why? Because SQL Lite says, well, you got the file. You must have had a password to get the file, so I'm not going to need one. Whereas this one says, no, I'm running a real server here. You may not have access to the data now. So, but this is like SQL Lite 3. That sits on top of Live PSQL, Live Postgres, just like Live SQL Lite, but it doesn't have the smarts to talk to the database in a file. It has to go off and actually make a connection to the server on another machine. And that's where we have a different piece of software running as well. This is a true separation of client and server. Okay? So the thing about this is, so this is going to be much easier. Instead of actually having, we're going to use, all these guys are going to use Live SQL Lite to get to an SQL Lite database. They're going to provide their own familiar set of tools for the users, but they're all going to be different. Okay? Okay? And we don't want everybody to have to learn how to connect and send instructions to Live SQL Lite. Okay? So they provide an API. We all bind to that. Okay? And unfortunately, it's that API, that C code that we talk to is different for every single database. So that means everybody has to go and grow one of these things. But that's fine. Oh, life is great. Okay, that's fine. Okay, so we do this depending on how many users we think they're going to actually be wanting to bother to do this, but it's all well and good. But now this is annoying because we actually have different code to talk to different databases, and that's bad news. So here we come with SQL, because otherwise every database, and this is the old days, every database you used to have to use a different language to actually get access to the table. You had to connect to it in different ways, but then you also had to talk to it in different ways. And every time you wrote a piece of code, and you wrote this piece of code, and your business was running on it, and then somebody had a great idea that the license for this database is too expensive, let's switch to another one. And then they said, that's great, look, we saved $25,000, and all we need to do is spend $2 million rewriting all our code. Okay, this is a net win for one manager and a massive loss for the other manager. Okay, and this is a real problem. So then people said, you know what, if we just had a language that was the same across all databases, then we would all be great. And then everyone said, that's great, but what should the language be? And then they discussed it for months and weeks and years and years and years, and they're still discussing it. Okay, but they come up and they all said, well, our database doesn't do that, so you can't make that obligatory. So then they went with the minimal set of functionality. And the good news is that's actually pretty powerful. But you can always use the non-standard functionality in the database, but then your code becomes non-portable to it when you switch databases, okay? So basically we have a single common database interface. For those of you who know Java, it's JDBC, Java Database Connectivity. In R, it's called DBI, Database Interface. In Python, it's DBAPI. This is basically saying, look, we want the same functions. We want to be able to call SQL, which is now standardized. We also want to have basically the same functions for different databases. It's one thing to be able to send the same instruction to different databases, but not if I actually have to, if I use different functions in Python or R for things. So we want to make all of this look the same, okay? And in R, this is going to be the DBI, okay? So here's how we connect to a database in R, okay? We're finally connected to a database, okay? On a slide, at least, okay? Okay, to install a package, what you're going to do is you're going to need to actually have client or database specific, a database engine specific package. So if you're connecting to an SQL Lite database, it's RSQL Lite. If it's an R Oracle or MySQL, it's R Oracle or MySQL or Postgres and so forth. Okay, you load that library, and now what you do is you have to actually create a database engine specific driver. This is the guy who knows how to connect to the database, okay? And this is what we do. We basically say, we'll do this in a second. There it is, library of RSQL Lite. We create a driver we call the SQL Lite function. Nearly always it's the same name as basically the package kind of idea and the database that the database type that we're connecting to. We create the driver. It doesn't say anything about where the database is or anything, and then we connect. I'm going to use this driver to connect to multiple databases, okay? Multiple different SQL Lite databases, that's fine. But basically what I say is then, please connect using this driver to this file, okay? This is an SQL Lite database, it's just a file. Okay, so I say, hey, here's the file, it's in my local directory, it's over there, it's over here, okay? So we can go off and we connect. Now we're done. We've now connected to the database, and that's the only database specific component to this. If I was doing something slightly different in Postgres, I would say library of our Postgres SQL. By the way, just to be clear here, if I want to install library of our Postgres, I'm probably going to have to install the client software for Postgres, not for R, but for Postgres, and then install our Postgres SQL. Okay, so that might get done implicitly for me, but it has to get done. So our Postgres sits on top of the client software, which then connects to the server. Okay, and so what we're doing is basically say, give me a driver for Postgres, the generic Postgres, I don't care what database it is, and now connect. Oh, and this time it's not a file name, it is the database name that's running on the server. And by the way, here's my password, because I know you're not going to let me in if I don't give you my password. And by the way, I may also have to say, and by the way, the machine, it's not running on my machine, it's running on this machine or this IP address or so forth. And it may be running on that particular port, it may be set up in different ways. But this is where, when I connect, I specify all the database server specific information. Everyone clear? No big deal, okay? I can run these. If you don't believe me, I can run. Okay, they're running on my machine. We can do this, and you can easily mimic all of this stuff yourself. If you are in any way skeptical about the client server stuff, run it on your own machine. I'll show you how to install it. Okay, it's really not a big deal. Okay, and now off we go. Okay, now basically this was very specific to our Postgres. Okay, we have to call that function, whereas over here we have to create the driver with SQL Lite. Unfortunately, that is specific to the database that we're talking to. Okay, but after this, we just use DB connect and DB connect. So it's the same verb, same functionality. We give it the driver that is specific. So if you were here last week, or the week before that, the week before we were talking about object-oriented programming, this is object-oriented programming. It knows what the class of this thing is and goes off and uses a different method. Right. Here, we also give a different argument because this only needs the name of the local file, whereas Postgres needs to tell us the name of the password, the name of the database, the login name, the password name. Okay. In this case, it's actually and then we may also need to specify the machine and so forth, but it's still the same verb, DB connect. Everyone happy? You can have many of these. I used to think at one point, I don't know why, because actually the person who wrote the DBI package, as I was just saying to Clark, about 17 or 18 years ago, it was a colleague of mine 2 doors down, And we never really played it. We didn't play with this often enough, but you can actually have connections to multiple databases, like to multiple SQL Lite databases, and talk to both of them simultaneously. Okay, and to 2 SQL Lite databases, 4 Postgres databases, 3 Oracle databases, and be connecting all the data and brokering everything yourself. The databases don't know about each other, but you can actually sit in the middle and talk to all of them concurrently. Okay, and that's fine. That's all there is to it. Okay, now the DBI package provides a bunch of abstract concepts which are related to SQL. Okay, so there's 2 things we're going to do. DBI says, how do we actually talk to the databases? What verbs do we use? There's only sort of 3 or 4, 10, okay, at most, but 3 or 4 important ones. And then what we say to the database, not how we talk to it, but what we say to it is all going to be all SQL, okay? So there are 2 different things because there's 2 pieces of software here, okay? So basically what we're going to do, DB get query sends a query, gets the result back, and we're done. Okay, we're back in R with the results in R, and we've separated from the database for now. We can go back and ask it for more, but we've got the data back. DB send query is another function, which is different. It's because it's got a send rather than get in there. That's the only difference. And what it says is send the results, sorry, send the query, send the command, and just leave it there. Let it go about its business. Okay, like drop it in the mailbox, send it off, and I'll come back and get the results later on and see what's going on. Yes?
I'm just trying to do what you're doing now on my computer. So I looked in the GitHub link that you sent us, and then I couldn't find it. I mean, the only R file that I find the GitHub link, it was RUBI.
I think there's some further down. There's some in the subdirectories, but we weren't looking at our files here. You can get there was none of the code I had here was there. Well, there's some lying around in our files, but they're probably lower down. But you can cut and paste this code. You can't do this because I'm running Postgres on my machine and you're not probably, and certainly you don't have an account called DTL. Okay, and then. And this one here, if you change this to be the presidential one, G presidential order /CO, that would work. I didn't commit the students because I didn't finish it. Okay, and the other one you don't want to touch, which is too big. Okay, well we can sort that out. But conceptually, I mean, these are all very important things, which is actually how to run this. But they actually do run. For once in my life, I actually tested them before I put them in the slides. So DB send query is basically the other way of talking to this. We send a query, we continue doing what we're doing. It takes hours to complete this query, probably seconds, okay, maybe even microseconds. And then we go, oh, great, we'll go back and pick up and say, give me the results. And we can say, give me all the results. Or we can actually say, give me the first 20 rows or the first 2 million rows. I'll deal with them and then I'll go back and deal with them later on if I so desire. Okay, maybe I'll decide I've got enough. Maybe I'll decide that I don't have time to process anymore. Okay, but I will go back and fetch them. So these are basically these are the 2 really important ones. And this one works just fine. It's just that if it takes a long time to get data and there's a lot of data coming back, this is going to be expensive. This is a nice way of actually saying, I'm going to take control over how the results come back. So this is a little bit more advanced, but very easy to use. We can also query all the metadata about what's in the database, what driver are you using, what tables are there, what results are available to us, and so forth. And we can create and drop tables and update tables. Again, I'm trying to stay away from you modifying the data. Yep.
But would you like to do the query but not with the results now? I mean, if I do the query now because I want to know the results.
Very impatient.
I mean, I don't know.
Because if it takes 2 hours for the results to come back. So if I send it to a database and the data are ridiculously complicated, and one of the computations that I'm doing in the database, in the query says go off and actually compute this really, really complicated thing for every row to see if should I actually get that row back. And then I might want to continue on doing what I'm doing. So I launch my task. So it's just like if you're running a simulation or if you're doing some experiment in a lab and you can leave it overnight, you don't stay there, do you?
Okay, but does it, when it's doing the query, so you send the query and it will work on it, but you still work on something else. Yeah. And
Do it in R.
okay, and if I ask them to give me the results at the moment, I cannot keep working.
Yeah, if you say DB get query, you go like, wait, my prompt will not come back because what I'm telling is only come back when that's got all the results.
It's basically like open like a different chain, and then you can work as you said in parallel.
Exactly. That's the theory. Okay, and it depends on the server and all that sort of stuff, but, and all the site details. But yeah, so it's kind of nice. And the other reason I want to do it, as I mentioned, I'll show you an example very soon. I know it's in the slides soon enough. I can't remember exactly how soon. Is what I also want to do is, if the results come back and there's 250 trillion rows, I don't want it. I just don't want it. I can't deal with them. Okay, it's going to flood the network, and it's going to actually flood the memory in R or Python or anything, because my poor little client can't deal with the capacity. But I can deal with them in small chunks. So what I'm going to actually deal with them is I'm going to say, give me, I look at the machine, and you can handle 500 million. Give me the first 500 million. I will then collapse them and compute a number. That's it. Okay, depends what I'm doing. Let's suppose I'm doing a regression. We can do regression one record at a time or block at a time. So I'm going to do this because I can't do it on all 250 trillion. So I'll just compute the summary statistics on this block, throw it away, and then ask for the next block, compute the summaries, update the summary statistics, throw it away, and I will never have more than 500 million records in memory. I can deal with that. Now I've actually been able to deal with the problem. Whereas if I go with this guy, okay, I go with DB get query, I only have one choice. Give me it all back right now, okay, or don't. Now, we'll see in a moment that I can actually say, give me back the first 500 lines, 500 million lines. I get those, and then I go, okay, give me the next 500 million lines. He goes, next from what? We stopped our conversation. I threw all the results away. You mean, give me the second set of 500 million lines if I have to do the whole thing again? And your database guy says, why are you doing the same thing over and over and over again? So this is a much more efficient way of actually being able to do this in chunks, okay? It's the same thing as we were talking about with sampling. You actually now going to pull in blocks. And this is why we actually need it. It serves two purposes: to be able to deal with things in smaller chunks than the overall size, as well as we can do it on our own schedule, where we sort of say, stop. You know, I want to continue doing something else. Yeah.
So does that mean with that asynchronous query, you're offloading the burden of carrying the results onto the server instead of on your own machine in that case? Because it would have to keep that active for whenever you come back.
It has to keep it active until I come back. This is why we run servers that are big, so that they have multiple. But if multiple clients are just, what's really annoying is if you basically, so if you do this, and when we do this, your web browser does this all the time. You keep an open connection to Google and all these websites, and there's a good reason for that, because it actually reduces the load on the server to actually establish the connection. But if you go, could you do this, and you never come back, that's just antisocial, okay? So so you should be cleaning up these results, and you should be disconnecting from the database. And then when you disconnect from the database, it says, you got these things lying around. I'm guessing you don't want them anymore. Off you go, okay? Yeah, so there is garbage collection. And unfortunately, just like in R, we know when you remove a variable, we can clean up the memory. Here, it's kind of it's disconnected, so we don't know. You may have just gone to sleep, and you may come back, or you may have gone away forever. So but we will try to disconnect, and then people will clean up. But there's no free lunch, unfortunately. Okay, everyone happy? So I started writing these down. I don't know why, because it's all in the documentation. In fact, actually, by adding text here, you can't see the first column as easily. So, but these are the functions that actually are of value. There's DB connect. We talked about just connecting. There's DB disconnect. That's your friend to actually say, I'm done with whatever's left over here. Okay, we like people to explicitly disconnect. Okay, it's a social responsible thing to do, as well as it actually it avoids errors when you actually do corrupt data in some weird way. There's a function here called DB list tables, and it will actually say, tell me the names of the tables in my database. This is really handy. Just give it back a character vector, it goes off and says, what are the names? So this allows you to query the metadata, essentially. You can also say, what are the fields in a table? So for a given table, tell me its fields. What are the names? And then DB read table is just a nice way of saying, go give me the whole contents of the table. That's actually going to issue an SQL command, which is select star from table and get the answer back. So it uses DB get query. It's just sitting on, it's just a convenience function. Okay, DB get query is what we just talked about. Fetch is the way I get back chunks of data from a DB send query. Okay, and so forth. That goes off down the bottom. Okay, so this is what we were doing. Okay, we DB list table will give me back the table names. Then I go off onto the students. Okay, I should not give you the students data. I do everything with students data. Then I switched over to the consumer presidential orders one. Okay, but don't worry too much. Sorry for the confusion. So basically now we can list the field and we get back some values, and then we can just say, go read me the table. Okay, these are just super high level things. This is just basically like read.csv. Okay, or it's like I'm saying, what are the columns in the CSV file? And how many rows? And so, well, we haven't got to how many rows. That's a snag. There isn't a way of saying how many rows are in the table. Okay, but we'll get there in a second. Okay, but this DB read table, that vals is now entirely in R. Each value in each record, so the entire row and column, has been converted back to native R objects. And if you change the values here, that's fine, but the database has no knowledge of that. These are two totally separate copies and independent versions of the data, okay? And if somebody changes the database 2 seconds later, you won't see those changes unless you go back and issue this command again, which is good. You don't want people just sort of changing things underneath you, but sometimes you do need to go back. Okay, so this is I say DBI is not very complicated. The DB query, DB get query, should I say, and DB send query, they basically take the same argument. You'll notice that everything takes the connection that we said. We got the driver, we did the DB connect, we use that connection everywhere, almost exclusively. I think always as the first argument in all functions. And then say, now do the thing. Here's the extra arguments. So go and get this query, which means send the query and wait for the answer and pull it all back and convert it to R. Okay, and then off we go. That's what we do. The query here, by the way, you notice is as a string. Okay, it's just a character vector, a character string in R, and R couldn't care less what you put in there. Okay, you can put in a letter to your mom, you can put in nonsense, and all that will happen is R will go, here you go, and then the database will get upset and will give you an error, and hopefully the error message will come back to R and be intelligible, but there's two people talking, and R, the DB get query, the DBI package, says, I don't understand the word these people are saying, but they said there was an error, and they said, here. That's it, okay? But I have no context in what you're doing. Okay, so we can put any string we want in here. It should probably be a legitimate one. Yeah.
I'm sorry, could you say that again? You said get an error, it'll show you that error on the prompt, but R won't know what it is.
R will say,
but it'll show it to you.
It'll show it to you. Okay. And it can be, and you know the way R error messages are cryptic? Well, this will take it to another level. Okay, so there's two people so saying, this guy said this. I don't know what it means. You don't know what it means. It doesn't know what it means. Okay, figure it out and then try again. Okay, so it can be very, very cryptic because you are talking to two systems, but R will just report whatever the database says back.
Do the keywords have to be capitalized?
No. But we do, because it makes it easier to read. But no, they do not have to be capitalized at all. But the keywords in SQL, the actual grammar that makes up the SQL command, those bits don't need to be. But that is the name of the table. That better be the right version. Okay, that should be spelled the same way as it is in the actual DB list tables and so forth. This here is the name of a column, okay, and that should be spelled the same way as it is in the column, okay. Some databases don't require that, but most do. In which case, just don't. You don't want to be surprised that way, where you're hours later going, jeez, I hadn't spelled it incorrectly. And then this here is an actual literal value. Notice, by the way, because this is an R string, I want to actually put something in quotes. I use single quotes inside double quotes. This is an R thing. It's got nothing to do with the database. But the database needs to see that D1 as a string, okay, when it gets across to the database, and that's SQL says that's a string. That's single quotes is a string, so that's good. Okay, so that's an example of a. This is an example of a marginally complicated SQL query in the sense that that's all we do here. Okay, this is what this is actually doing is saying, go get me, what does the star mean? It means everything, every column. Okay, and the select command basically says select, what would you like? What columns would you like? The next bit is what columns would you like? I would like all of them, please, and I'm not going to type them out for you because I'm too lazy. Okay, yes, but I have lots of tables. Which columns would you like? In this case, it's quite simple because we're only asking for one table. Okay, I would like them from students. Okay, that's great. And if we just let's leave that aside for the moment, and I just get back every row with every column. Okay, and it comes back as a data frame in R. Now, if I say, you know what? I don't want every row. I want to limit this to only the rows where the value of the stage variable is equal to D1. And this is just a subsetting operation, okay? So this is getting me the columns, and this is getting the rows, okay? The ones of interest, yeah?
I did a little test when the deal is not in the table. It gives you actually an empty row, but with all the columns.
Which is what?
Like a D1 was not actually in there. It gives you all the columns, but empty rows.
We'll have to. Well, we can take a look. Okay. Okay. We can. It's. I'm saying the clock. I don't know what you've done before. So but SQL has some interesting characteristics too about missing values and nulls and some interesting things. But it normally does the logic thing. We also have to check which version of the database we're actually using.
So stage would be like a column name, for instance.
Yeah. So unfortunately, I switched my examples over. Didn't fully think so. I can do this live with another database. We'll do it with the president's orders, and where I have that all set up to be live, and that's fine. We can go through these things, and that's exactly what we can do. But yeah, in that case, stage. By the way, what's D1 and stage mean? What does D1 mean? Are you D1 or D2? I'm talking to you. You're a D1, okay? So we have these classes of PhD students at D1, you become a D2, and you actually pass your qualifying exam and submit that. We want you to submit that form as soon as possible. So yeah, so this is that. So the stage is just actually what level of a PhD student is. So it's a variable that we have in the table, exactly. So as we go back here, this is the syntax, this is select, and we tend to use capital letters to make it very clear as to just so easier to read. So that's harder to type, easier to read. It says, I'm selecting what from students. This is the table where this is a variable, and this is a logical condition on the rows. And I can put in multiple tables, and I can have columns from multiple tables, and I can have conditions across tables. I can do all sorts of very obvious, simple things. So we digress now, okay? I'm gonna go to a different set of slides, okay? This is SQL. We will now go through this quickly, okay? But tell me, ask any questions you want. I just find SQL to be actually very simple. I mean, not that it's hard to reason about, it's complicated enough, but in terms of actually the amount of things you actually have to go through, is not very much, there's not much to it. Select star from orders, select, I only want one column here, just give me the amount column from orders, give me amount and order date as 2 columns from orders. There we go, okay? So this is how I pull out columns, okay? And everything is built off of the select command, okay? And it gets heavily used, okay? We deploy it for various different operations, but that's nice. It's just a single verb essentially, which is always going to tell me which columns you want back from what, and then tell me some extra things about what you'd like me to do to filter out the results. And we can also do some other things. So where we put in conditions like where the amount is greater than 100, okay? Yes.
When you do the query and you get the results, do you get like a simple table data set that you cannot relate to, so that it doesn't have any key anymore?
It does. It will have a key.
So it will still
So let's go over here, and So this is what we were doing in SQL Lite 3. We can go off and do it if I remember where I am now. I think so. Let's do this library of RSQL Lite, just okay, and then we will do what was this? We will do DB connect of SQL Lite CO here. Okay, and this is going to be my database. I'll call it a connection because I keep on changing it. Okay. Again, I'm just now, for those of you who aren't familiar with my setup, this is just R. I'm just running R inside a terminal, inside Emacs, inside a terminal. Okay, what could be simpler? Okay, but it's just regular R. Okay, there's nothing complicated. There's nothing. This is your same R. Okay, so now if I do the following and I say DB get query, again, I'm not going to wait for the answer. So now I'm just going to say select star. Well, let's just do this. DB list tables of con, just always check where I am, okay? I do have those two tables. I am talking to the right database, okay? DB get query of con of select star, as I say star, say it's from orders, let's say. By the way, you need a, what are we talking about here? So this is, let's just call this O. By the way, you need a semicolon on the end of every single SQL command, unless you're in R. Okay, you don't need a semicolon. It depends on who you're talking to. If I'm talking to SQL Lite 3, it says you need to tell me when I should send the command. Whereas R is saying you're telling me to send the command, but it's string, so we don't need the semicolon. But there's no harm in putting the semicolon here too. So this is O. So this is the result of O. So and again, what is the class of O? It's got nothing to do with the database. It is a data frame. And if I run over at this and I say, what are the classes of this? The classes are integer, character, numeric, integer. These are the actual R copies of the database. But the keys are still here. The key between these two databases, just to be clear, I want to show you these, which is, let's go and get the other guy. Let's go and get the customer database. I showed you the orders earlier, but okay, and this is C. So this is another. This is a record. This is one record that spans 2 lines. Okay, this is the customer ID, and this is the customer ID. So I pull this from a nice simple website that tries to describe this. We all use various different really small data sets so that you can really go through and reason about what is coming back. Okay, so what we're basically saying is this person, George Washington, okay, who's customer ID 1, made this order. So we're going to connect the keys this way, just like the actors and movies. This is the magic key, the customer ID and the customer ID here. This is a primary key here, okay? And then this is a foreign key over here for those of you who care. And if you don't care, you're just as well off, okay? It's obvious how we're going to connect them. If you look at the schema, you can actually see what are keys that are connecting the pieces. You kind of need to know how to join the rows or connect the rows, but you don't need to know that they're primary and foreign keys. You just need to know that this key here connects to this key here. Oftentimes, but not necessarily, we will use the same name for the column so that it's clear that they are connected to each other. Okay, these guys here, notice here, these guys have to be unique. You're not allowed to have 2 customers with the same key. It is a train wreck. We will never be able to disambiguate between those 2 people. They can have the same name. First name, last name, date of birth. They can be identical the whole way across, but not in the key. And sometimes we can actually do this where we basically say the first name and last name may be the same. Their emails can't. We could use these 3 things. Okay, but we like to have unique column keys to make. I do for making things simple to understand. Okay, but basically, so these are unique, but these are not unique. This person, who's number 3, that's number 3, Thomas Jefferson, made 2 orders. Okay? And in this data set, by the way, just for fun, these 2 guys do not exist in the customer database. That's okay. No, there's no harm in that, but we still have the keys. We ask for everything, so we still have the key. They're pretty much useless to us at this point. Well, they're not, because what I can do now is I have pulled this back into R, and I pulled it back into, I pulled the customers and the order database into R. So I can now do the joins myself, and I can leave the database alone, okay? And that's what a lot of people do, is it's just give me the database and get out of the way, okay? So you can loop over the DB list tables, the names of the tables, get everything back and say, now disconnect. I want no help from you, Mr. Database, okay? But when the data are huge, or when there's 12 million tables, and you have to start doing all these matches by hand, okay, happy?
Yes, I was wondering if this is like the same as you have an access database and you extract each of the tables as X files or CSV.
Yeah.
And then you download that in app. It would be exactly the same. But here you can do everything in app.
Here we can do everything in R, but we can do so much more because that's it. You've now got a lot of redundant. Well, you're going to have to do a lot of matching across. So in a lot of cases, what some people will do in this thing, you can download individual tables, but I actually want to know. I'm really not that interested in customer ID 1. Okay, I want to know who the name is. This is an internal detail for the database. Okay, I mean, oh good, customer ID 3 bought 2 things, totaling whatever it is, totaling $143. Whoa, we should go after him. Okay, what's his name? Where does he live? What zip code is he? I want to know this. Well, I have to go down and do this. So this is the whole point of databases. We now need to join the data for these rows with the corresponding rows here. Okay, that's the magic piece. When you're going to do this, if I dump these 2 separately, I am left doing this. Okay, and that gets just tedious. And those of you, I asked how many people match. That's what you're going to have to use. And there are functions that will hide this. But when you want to do some complicated operations, you're going to have to actually figure out how to match things. So how do you match? So a match is a really interesting function in R. After I've been using R for however many years, I think I now understand. I think I now remember which direction it goes. You match this into that, as opposed to that into this. And well, my head explodes. So I actually sat down, and I'll show you later on. I actually sat down and wrote the commands in R using match to do the different types of joins. And it's a really good exercise, but you do have to concentrate. So it's much nicer to leave the database do it for you and just say, oh, join them and be reliable.
I mean, like, I think, isn't that the problem? Matches that it only finds like the first instance.
No.
Yeah.
Depends on how you do it. We can use match to do this, but you do have to think hard, and this is why the database is nice. It actually is trying to abstract out a little bit for you. But okay, and then R functions. There are functions to hide this too, so it's fine. But the R functions can use databases, but we can use SQL to do the database, to do the operations too. So whether you decide to just pull the data out of the database or leave it in the database and do the queries there is up to you. Totally, you're spoiled for choice as opposed to having only one choice, which is get them out into a CSV file and then do all the manipulation yourself. Okay, so this is all very simple. By the way, notice single equal sign for equals. Okay, not 2 equals. This is not R. So this is one of the joys of writing in 2 languages when you're actually writing the command in R to run somewhere else and you start using the wrong syntax and then you don't understand because the error message comes back and it says, I don't understand you, and you go like, oh, wrong language. Okay, we intuited, as I said, the equals and the greater sign, obvious, okay? And they also have the less than, the greater than, equal to, less than, equal to, and the not equal to, which is different from R, not equal and different from Python. This is, okay, less than, greater than sign. Or you actually have a not operator, the actual word NOT. Okay, so we can basically do the same. We also have an in operator, which is very much like R. We say select all the columns from customer where the first name is in John or James. This is the sound. We could write this out as first name equals John, capital OR, just because we use capital letters, but it could just OR. Okay, but I haven't told you about the ands and the ors because we haven't got to conjunctions yet. So this is just another operator, if you will. We also have this hideous thing, but that's useful, but not that useful, which is you can do string comparisons. For those of you who are familiar with regular expressions, this has got nothing to do with regular expressions, and it's woefully underpowered. Okay, this is an example of the compromise between the SQL standard that says we can't do that in our database, and everyone goes, okay, well, this is the minimal thing you have to be able to do. So the like, basically, we can sort of say, go find all the zip codes that start with 22 and then have any number of characters after them. Okay, so it's a very simple thing. It's very confusing too. How many of you have ever seen the % character used for any number of characters? We're familiar with the shell with star. We're familiar with regular expressions of dot star, %. Oh, that's great. That's really helpful. Now I have to learn yet another one. But there are variations of these that are reasonably standard. And then you can do this between, so it's like in, less than 2, and greater than -1 or whatever it is. We can do these different things. Life is good, okay? But that's the same thing as an and or an or. We really could do the same thing there. So this is some, there are some syntactic conveniences, okay? But usually I like to focus on the primitives, okay? Okay, there's the like is case insensitive. That's really annoying. Okay, it may be, it may not be, depending on the database. There's a lot of non-portability here. The SQL is reasonably standard, but not entirely standard. More to the point, we have lots of SQL standards, SQL 89 and so forth. You have to ask your database what standard it's actually complying with, and then is it actually complying with it? You may need to escape special symbols as a way of doing that, not just a slash. Remember in R, when you have to, in a regular expressions, when you have to escape the parentheses or a star, you put 2 slashes in. And if you want to escape a slash, you have to put in 4 slashes. Now you're sending it to a database, which also needs escapes. So trying to understand how to escape these things, there is an actual escape operator in some of these databases. So anyway, there are workarounds. You have to read the documentation. You are getting into things that are actually non-standard. So that what we do, select star, the columns from this. Then we said, where is filtering by row? We said there are these operators you can do on single conditions. Now we can combine conditions. There's an and, there's an or, and there's a not. So you say, and is greater than 1, and customer ID is equal to 1. Where first name is James or the last name is Adams, we'll pull out, okay, an or condition on that. All, I think, very straightforward, yeah? I mean, stop me if you have any questions on this, but it's hopefully pretty straightforward. The grammar is intentionally very simple. It's just the select from the entered columns, and then we tag on this, the from customer. So this first bit, the tables, and maybe multiple tables here. Maybe just comma separate customer, comma orders if that's relevant. Then where not state equals VA. Just now we're filtering. There's one extra bit we're going to get to. This is very useful. You can do the following. This is the bit that seems slightly weird. Every time I look at this, I'm like, it's clearly done by a committee that sort of couldn't have to accommodate certain things, and you can see them. But if we wanted to actually take a look and sort of say, we wanted to look at this data, suppose we actually wanted to where we only wanted one value from each of the customer IDs. Okay, so for whatever reason, we don't want all of the data. We just want distinct values of customer ID or distinct dates, okay, or so forth, okay? Then we could actually just say, give me back the customer ID, but make them distinct. Drop duplicates, okay? So whenever you see one that's already come back in the results set, just drop it, okay? That's fine. So this just arranges for distinct records or results, not distinct customer IDs. In this case, there's only customer ID coming back. But if I ask for 2 variables, like customer ID and date, then they both cells have to have been seen together in exactly the same place, okay? So A and B and A and C are not distinct, okay? Even though A and A are duplicate, okay? A and A, if I'm just asking for A for one column, and I get an A and I get an A, I don't see the second A. But if A and B are not distinct, are distinct. Okay, so it's a multivariate thing. It's actually every cell in the result has to have been seen in identical order in the previous one. So we're looking for unique rows here, not unique cells. This is also useful to be able to say, give me all of the rows, but limit it to only 2. Why do I care about that?
If there were 500 million, you wouldn't want them.
If there's 500 million and I don't know how to filter them down to the ones I want, I just say, just give them to me, and then I just want to look at. So this is like head in R. You just give me the first 5, whatever it is. Okay, and that can be useful. It also can be very useful if I actually order them, and then just take out the top 5. Okay, so what we can actually do is instead of, in addition to limit, we can order by. Okay, so now we can order by 1 or 2 or 3 columns. Okay, so this will order by amount. If we get a duplicate amount, we'll use the next column value to actually to rank within that, and so forth. So what we can actually do is we can say order by and then limit to the first 10, which will give me the top 10, okay, or the bottom 10 in this particular case. So then we can change the order by which we sort, which is by descent. So decreasing, descending is what this is. So we have to remember this. So we can limit, we can order by, and then limit, and then we can also change the ordering that we get. Okay, the database will take care of all of this for us. And you know what? If you were to do this in R, what would actually happen is you would basically say, go get me this subset. So you would say, give me these columns from orders. So you say orders, square bracket. So what would you do? You would actually do this. Okay, you would say orders. It doesn't really matter here. But you say orders, square bracket. Okay, and you say, give me everything. So you put this thing in here. What are we doing? There is no limit here. We just get all of this. So maybe we say where the amount is greater than 100. Okay, we got 200 million things coming flying by here. Okay, so this is, unfortunately, as I was writing these, I'm using the word orders, and I'm going to use the word order in a second, which is now entirely to do with R. Okay, but we would do this. What R would do is it would actually get this subset, and then we would say, now, can you just reorganize it? So we would put this into temp, and then we would say temp, square bracket, order, temp, dollar amount, let's say. Okay. Okay, so we're gonna get the 200 million, and then we're going to actually flip around. So this takes up 100 gigabytes. We're going to make a copy of it. That's 200 gigabytes for those of you counting. Okay, and then we throw away, and then we just say, give me the first 10 elements. That's an awful lot of computation. This database is smart. So if you take a class in databases like ECS 165, okay. A lot of people will say, I want to learn about SQL. So I want to take ECS 165. And I say, no, you don't. And they go, yeah, I do. And they spend 2 weeks. We can do this all in 2 hours. Okay. And they go, yeah, but that's the right version. What they're learning how to do is how to implement this query cleverly, where they don't actually make 2 copies of everything. What they're doing is they're going through one at a time. Going, yep, okay, that's it. That's in the top. That's in the top. Now it's dropped out of the top. We'll throw this away. We keep. It actually dynamically builds up the small results set and only ever have 10 records in memory at most, because it knows what the goal is. Poor R is too stupid to actually look ahead and say, you did this, and then you did this, and then you sort of set it over here. R goes, I'll do one thing at a time, and then I'll see if you've changed your mind. Okay? And whereas the database, well, the beauty of the database is it's actually extremely smart. It takes your query, it wants the whole string, and says, I am going to make a plan for this. And it can spend actually a couple of seconds making a plan if it thinks it's going to save a vast amount of time. Okay, it's essentially compiling the code. Okay, but it's such a simple language, it's easy to compile. Okay, so that's one of the benefits of actually leaving this to the database. Okay, so therefore, okay, off we go. Okay, so this is actually, so why are we using qualifiers? This is fine. These are the two same thing. What does this do? This is a simpler example of what I was just describing over here. This says, give me back the 8 terabytes of the column of this table, and then give me the first 200 kilobytes. You go like, that was an awful lot of computation, an awful lot of data transfer to throw away almost everything. So this is a much more efficient way of doing this. And this guy may not even look. In this particular case, this guy will not even look at anything more than 50 rows of the table. It can actually go, depending on how this is indexed, it will go directly to the first 50 rows and stop dead and never actually bother visiting the whole table. Whereas this will actually visit the whole table, and then this will actually throw it all away in another language, and that hence has done a huge data transfer. So we are essentially doing parallel computing. There's 2 people in conversation here, R and the database. And a big aspect that Clark is working as he's stuffing his face in the kitchen, a big part of the, I tease him a lot, a big part of what we want to do is minimize the data transfer and do the computations locally where the data are. this actually will require, this benefits from some thought. Same thing with the ordering here. So limiting or ordering, you want to think about where you want to do the actual subsetting and limiting and ordering, because if the database can do it, let it do it. Okay. Missing values. R is very special about missing values. It has NA all built into the whole system. Databases have no concept of missing values. They just have null, if you will. Okay, and they don't really know why. Null can be an actual. It's almost never used as a legitimate value, so it corresponds almost directly to NAs. Okay, but not 100%, but close enough. Okay, so when somebody doesn't provide a cell for a row or record, it becomes null, and that's what we're going to get back later on, okay? And it'll come back. And the nice thing about that is null in R is not a number. It's not an integer, it's not a character, it's a special object. So when they come back in, and we know the schema type, we know the column is integer values. When we see a null there, we put an NA in for R. So the nulls will come back as NAs, okay?
What if it's in a database?
The actual name NA, then the only way to get an NA into the database is to actually have it as a string, a varchar or a char, which is NA, okay? And R will then keep that as a string whose value is NA, which is different from so it's a string whose contents are N followed by A, which is the state abbreviation for?
What?
NA, state abbreviation for? Nebraska. It's Nebraska. So NA is a perfectly legitimate value, okay, as a state name, as a state abbreviation for Nebraska. But that's why when it's outside the quotes, it's a variable who's very special in R, which is it's a missing value. But it'll come back in there. The only way to get it into the database is as NA, is as a string NA, because it doesn't have the concept of that. But this is the weird thing that's where you're mapping from one system to the other. Okay, everyone happy so far? No?
So is there not
okay, well, you get what you pay for.
so there's not like a function in SQL to just select a random number of rows?
No. It doesn't have that concept. It just does not have that. It's not built into the relational algebra. It's not built into the notion of what's called a cursor, where it knows where it's at and all that stuff. No, it's not. Now, but you'd like to be able to sample that way, kind of idea. So if it's above some threshold, we can do that where we can actually sort of stick a number in, okay, and we can actually say, are you in the sample that I want? And we'll talk about that a little bit very soon, okay? You can do some clever things that SQL can't do because we're in R, and specifically we'll get there in a little bit, okay, in about 7 or 8 slides. We'll get there, which is, you can be really clever about the string you create to send to the database by encoding a lot of information that the SQL database cannot do itself. So you can mix the two languages to great effect. Okay, and if you're good, so the thing about it is, one of the things, if we were going to get it back into this, in terms of the relational algebra, there's a massive distinction between a data frame in R and a table in SQL. They both have columns and they both have rows, records. The database has types. We kind of have implicit types. They have explicit types. You can't stick a value in that's got the wrong type. It'll be an error. There's one other really important, very subtle distinction, which is important. Anyone guess what it is?
Data frames are temporary, but the tables are permanent.
No, not really. That R is temporary in the sense it goes away. The database can go away, but they save it to disk. We save it to disk. So it's much more subtle than that. But I understand what you're saying. We tend to think of the server living on, but those SQL Lite guys are just like R. They go to sleep and they write to disk and then they come back again. And R, we save to disk. So that's fine. No, it's a very subtle distinction.
Because data frames are just like an inherent order.
They have an order. We implicitly assume, and it's normally true, that 1 and 2 and 3 correspond observations 1, 2, and 3. If we have another database, another table that has the same length, maybe they correspond. Maybe they don't. Maybe oftentimes they don't, but there is an order to them. It's not important. We don't exploit this a lot, but the database says there cannot be an order. Okay, you cannot rely on the order, and that's a part of the problem. So you can put an order on, like actually giving them your 1, your 2, your 3, and if we actually create a column like that, then we can do some interesting operations. But the relational algebra says there cannot be an order to this. You cannot expect me to actually visit them in any particular structure. Okay. So this is the world's stupidest language because it doesn't have functions. Okay, it just says select star from where, okay, and all that stuff. But it does have a few functions. Okay, but it actually does have functions. It's hard to write functions. It's not like R or Python where you just write your own functions. Although you can, we'll get there in a moment. Okay, but it has 3 different types of functions, but they're very simple. Okay, the whole point of SQL is it's intended to be simple, a nice, clean, simple, no frills, no new features that bog it down and make it too complicated to reason about. The 2 types of functions that we care about are record functions. So they work record at a time. They get given a record or values, cells from a single record. Okay, so they get the amount, a single amount for record. They do something and they give back another value that we stick into a column. They can't really return multiple things. They can't return 2 things. They have to return 1 cell value. Okay? Okay, so these are things like the log function, okay, the sign function, add addition function, add this value with this, okay? And they can take different columns, they can take literal values and so forth, that's great. We also have these aggregate functions, which we haven't got to quite yet, which is what they'll come up soon, okay, but I'm just introducing them here, where we do this group by. Instead of actually doing record by record, we want them to visit each record. We want them to say, give me the record, I'll update some number or some value, okay? And then at the end, when I've finished all the records, you can ask me what the result is. So things like the mean, okay? I will actually keep a running total and how many things I've seen. When you ask me for the answer, I'll divide the total by the number of records, and then we'll move on. Okay, so in those cases, we'll call them multiple times, each time with 1 record, but then we call it again at the end and say, what was your answer? Okay, so these are aggregate functions because we're collapsing across a subset. We use those in group bys all the time. And then there's triggers, which are really helpful for those people who actually administer databases. Okay, SQL Lite, if you take a look at it, has a few functions, a very minimal set of functions. If you take a look at the Postgres functions, they're voluminous, okay? So that's the problem. These are non-portable, but you can add functions to SQL Lite and to Postgres and other things, and then it becomes interesting as to whether or not where do we do the computations, okay? It's hard to rely on these because they are non-standard. They behave in a non-standard way. They take non-standard arguments in non-standard order. This is the Wild West. Okay, it's a pain, but they're really useful, especially because, as I say, I'll get to this soon, which is there are times when you want to do the computations entirely in the database so that you actually end up with a much smaller set of data as a result to come back, as opposed to doing the computations back in R. So it'd be nice if the functions were there and we can actually add some. I'll show you some later on, which is more advanced. Well, not more advanced, but more esoteric stuff. But it's fun. Okay. So basically here, this is an actual function called star. It's arithmetic, but we're just multiplying by the tax rate to get the total. Okay. Okay, and life is good here. So select amount star from orders. We're rounding this value down, up or down to be an integer. We're taking a substring from only the first 5. And notice, so this is actually, we're saying select. So these are the columns I want from these tables. What are we getting? We're actually doing computations on the actual cells coming through each record. And they're going back into the results. And here I'm only asking for 1 column back in each of these. And what's really weird is, what's the name of the column here? And my result set?
Is it the same place as the amount?
It's going to be amount star. It takes this literally and just says, that's your name. Okay, it's like, okay, fair enough, that's a useful name. Okay, so that's kind of actually where it's kind of annoying. So we do this. Okay, select amount has that name. The actual name in R will be amount star 1075. It won't have the exclamation mark. I added that. Okay. Okay. So what we do is this: select this computation, but rename it. So as this name, please. from orders, okay? And later on, we can actually even refer in the query, later on in the query, we even refer to the result being called tax total. So again, it looks through the whole thing. Unlike R, it looks through the whole thing and says, I have a big plan for you, and you're referring to tax total later on in the query, that's good. But when this result comes back to R, it will be tax total as the name as opposed to the goofy name, okay? Okay, so you can do this. You don't even have, it doesn't have to be a computation. You could say, the person who created the database used a stupid name. I'm going to rename this when it comes back to me. There's just a strict case. You can do that in R too, but you can do it in the database. Okay, whatever is most convenient. Okay, so this for example, if you take a look at the customer database, we have dates in terms of month / date, day / year. This is a way of pulling out the month. Okay, so you can do simple things, but there's no date function. That's not how we want to deal with dates. Okay, it doesn't handle time zones for times. It doesn't handle leap years. This is just kind of nutty. Okay, so we probably want more powerful things. This is where you bring it back to R. SQL Lite has a few built-in functions. The extensions are fun. Okay, but there are a lot. You should look around if you're using SQL Lite. The reason I'm talking about SQL Lite a lot is it's so easy to get started. There's no client-server setup and permissions and no security issues, but it's not a very powerful database, but it's powerful enough for most people until they grow out of it. Okay. Okay. So these aggregate functions, the most important one is this. Clark and Nick are teaching a workshop this afternoon from 2 to 4 on elementary SQL. So if you want to come to that, you're welcome to have a whole day of SQL. But I'm going to go through a bunch of examples and sort of interactive typing and people running stuff, which I'm avoiding at the moment. One of the things we were trying to figure out is they were trying to stay away on the first day of this for our undergrads, staying away from functions. And I'd say, but don't people want to know how many rows there are? So isn't the first thing when you get a data set is you say how many rows there are, how many columns there are, what's the mean, what's the summary? We should always be doing this when you load a data set. Just tell me about the value, not the content, not the actual structure. So this is what we do the second I get a database, is I say select count star from orders. This tells me the number of rows, okay? And this is an aggregate function because it's basically going through row at a time and saying, yep, one, add one, add one, add one, add one, add one. No more rows. We asked for the answer. It says, there's the total, okay? So it's actually an aggregate function because it's not giving me back a value for each cell or for each record. It's giving me back one answer in total for the records I'm running through. What we do here is we're just saying, give me the min. So we say min amount as min, max amount as max. So we're just relabeling these from orders and so forth. Everyone happy? These are just, then again, this is what we live off of. Okay, so when we're doing this in R, this is the command, we just talked about SQL. Okay, now we're going SQL back to R again. So now we're saying select log of X from table. By the way, this will fall over, I think, in SQL Lite. It doesn't have a log function. Okay, so come on, you have to have a log function. No. Okay, so this is the other thing. Okay, B is equal to go get the table, go get the column, and then do the log in R. These should be equivalent. One may not be possible because the function may not be built into the database. In other cases, it will. So you have a choice as to which to do it, which is likely to be better. Certainly, if the database doesn't have the log function, the other one's guaranteed to be better. If getting an answer is deemed better, okay. So that's good. So, but if they both have something, it kind of depends. If the R function is vectorized, so it could be a very fast function in R. So you're better off to grab everything back and then just run it on the entire block in R. If the function is not vectorized in R, it's likely to be faster in the database, okay? Because you're just doing it cell by cell, whereas in R, we'll have to loop or do something. So you actually have to start thinking about efficiency if you care. Again, it's only if you actually care, okay? But this one is different. What's different about this? Here I'm computing the log of X from a table where X is greater than 0, as opposed to here, I'm computing X and the log of X, and then I'm subsetting here.
in the pyramid.
So I'm getting all of the data, and then I'm filtering it back in R. There's something else. There's one other little, again, probably not consequential thing, but what else is going wrong here?
I don't know, because people have imaginary numbers.
So the problem is, we're actually saying, don't do this. Don't compute the log of x for anything where x is less than or equal to 0. Whereas here we're saying, just go ahead and do it. Get nonsense. Fall over. Get an error. I don't know what you're going to do. I have nothing. But this says, don't even bother doing this, because again, this is different from R, where in R we would say, go do this, get the entire table, and then do the subsetting. This is doing the subsetting before it gets the table, in which case it's never actually going to compute the log of x on something where x is stupid. Okay? So there's actually two subtle things going on here. Doing stuff in the database is actually just a good thing if possible. And this is our group by operation. Okay? This is the key to databases. Select customer ID, same usual thing. What columns do I want? I can apply a function. The only difference to this, the only change we're doing here is we're saying instead of summing the amount across all records in the table or all the records that are filtering via the where command, we are now saying, oh, by the way, could you break them up? Could you do a split and apply and an apply? Okay, this is a T apply, where we're basically saying group. Go get all of the results, and if there's a where in here, the where will get run first to filter them. Now, subset them into groups based on the customer ID. So we get two for whoever it was that had number 3 had customer ID 3 had 2 records in here. So okay, and then we put them into buckets, and then we will shoot through and actually compute the sum of the total of the amount. So we'll actually get we'll get essentially their bill, okay, for each customer ID. And again, this is very fast. In fact, it won't split them like R does. R doesn't actually do that. It won't group them into buckets and then go visit them all again. It visits them cleverly, okay, one at a time, and figures out which bucket to put the answer into, or which answer to update. Okay, so this can be very, very fast. And this is why we like databases. They're so simple that they're very fast. This is why we like Fortran. It's so simple, it's very fast. It's just too simple for certain things, but hey, it's great. Okay, so we often do this where we basically do this and then we order the results by this, so we now see who owes the most amount of money. Okay, that sort of thing. So we can combine these into getting nice reports and results as we want, or we can do the computations in R. So what I want to do here is this. Show me this. Give me the customer ID and give me the amount, the total amount from the orders. Okay, so I do this group by. Okay, forget about the ordering by at this point. Okay, so let's look up here. Now, I want to restrict the results so that I'm only looking at people who have a total amount greater than 100. How do I do that? So if I say now where, I would put in where what, so where, okay, so I'd say where greater than 100. There's a little piece missing. Where, what is that piece missing? So I need a total. So I could say sum of amount, and I could say as total, okay? Actually, even if I say where sum of the amount, because it's smart enough to say, hey, you're doing the same thing in 2 places, even though you didn't give it a name. I know you're doing the same thing, so I'll do that. So we can say where sum of the amount is greater than 100. And that won't work. The where is for filtering the first table, okay? It's for filtering the orders, not for filtering the results. So we've kind of got our hands tied here. It makes perfect sense to put there.
Well, what if you put another outside?
So that will be a subquery, okay? And we could do that, and we could definitely do that. But not all databases handle subqueries, but we'll talk about those soon. But okay, but the answer is you could do a subquery where you basically select this, okay, from this other table that I'm just computing right now, and then do a where on that. But because not all databases handle subqueries because they're a little tricky to implement, we have this notion of a thing. They added a concept saying have it, and this is a where for the result. Okay, it's just what it is. It's kind of, this isn't elegant. This is but it's fine because you think of where it would be here. Some queries make perfect sense, but they are more complicated. Okay, so that's kind of nice. That is in my, so there's a lot of extra stuff in SQL. I don't have my book with me. It's in my, there's a great book, fun book, which is SQL for Smarties as opposed to dummies. Okay, which is kind of nice and it's really cool. Okay, and there's lots of stuff. There's another book that I have, which is yay big, of the MySQL cookbook. You know, there's just an infinite amount we can talk about databases and SQL. But the trouble is, they're all after this, they start becoming non-standard, and you start relying on features that you can't. That if you switch databases, you can't rely on them being there or behaving the same way. But this is all we. So this is basically what we have. Okay, and so that's why I was saying. So I got this into 17 pages of very little, because there's very little to it. Okay, in my opinion. So now, where were we? Let's go back over to here. So what I wanted to just do here, and again, I'm more than happy to go through. We can run stuff if you so desire. I'm happy just to do it any way you want. Okay, so let's go back here again. So this is where we stopped. We're now, okay. So there's this thing where we can determine types. This is not really that important. They're pretty obvious, okay? Okay, so that's fine. So this is the synchronous and asynchronous. This is the DB send query and DB get query difference. Okay, so basically this is what we do. We get the query, just sends the query, waits, returns the results. Send query says ends query, sends query, and then returns immediately, leaves that to work. Now this is, if you think about parallel computing, going back, if I got 4 databases, okay, and I need the results from all of them, I can say, you do this, you do this, you do this, you do this. I'll come back and get you. When the last one of you is finished, I will assemble the results. So this is parallel computing as well. It allows us to keep doing something else in R, but it also means we can talk to other databases or go off and scrape the web or whatever it is to get the extra data. Okay. What we get back here is a result or a result set. Okay. And it's a holder for where the results will start getting collected. It doesn't. It's okay. We go back and say, what do you have now? What do you have now? Okay, and then basically we get to fetch k rows. Okay, this did not format correctly. Missing a couple of quotes or something. Fetch. Actually, it's the only one with while. And here, what is going on there? I'm not seeing what's wrong. There we go. Okay, so this is basically when you send this query, it's huge. Okay, and now we basically say, okay, while the number of rows in my next result that I get, so I fetch, in this case I'm fetching 1 row, pretty stupid, okay? But I could change this to k, I could change it to any number I want. This is where the magic trade-off is. The bigger the block size, the more memory I use. The bigger the block size, the fewer iterations of the loop. That's a trade-off depending on my machines. But basically we fetch this number of rows from the current set. If there's none left, I'm done. Okay, that's not quite true, but okay. But that's a way to do it. And then I basically update my result. I do something. I add them to the plot. I update my regression estimates, or I do whatever I want to do. Okay, I do my sampling if I want here. Okay, everyone happy with this? This is just a very straightforward sort of. This is how we do it. So all you're doing now is you're basically saying, I've got a hose pipe, I can start reading as many things as I want. For those of you who know about connections in R, this is like opening a file. The difference is read.csv will read the whole thing and give you the results back. Whereas if you open a connection and then start reading them, you basically continue on from where you left off the last time. You can do things as sort of streaming data. Okay? It is an interesting thing. Rather than actually ask how many rows are currently available, this is better. Have you completed? Which is basically said, have I exhausted all of the results? It is possible that there's, basically, this shouldn't happen, but basically, you can fetch, and you could be in this weird state where it hasn't actually got any more rows, but it hasn't finished doing the completion. Okay, in that case, it should block. Okay, so we may say, give me the next 10 rows, and it says, well, I've only got 2. I have to wait for the next 8, okay, or until I finish. And now we're blocking. Now the whole point of us actually doing this asynchronously is gone because we're actually now waiting for another 8 rows or the completion of the query, which may take another couple of hours. So this thing here, DB has completed, says Have you completed? Which means, are you still working, or have I exhausted all of them? Have I consumed all the output? Okay, which is a subtly different thing, which is very important. This will say, no, I don't have any more results, but there are still computations going. There may be more, but you can keep going. You can go about your business and come back and ask me later. This says wait until I get 1 row or 10 rows. Okay, so this is one of the things I just wanted to hang on a second. I just want to. This seems to have gone off the edge, so I will just do this. Okay, so this, so here's this sort of thing. Because this is a string we're sending across, I'm now going to construct the string in R. Okay, I can type it in R, but you can actually build a string in R. So what I can basically do is I can say, pick a threshold between low and high, okay? So some number. Pick a random number, and anything above that I'll include, and anything below that I won't include. So I pick a random number, and now I say select star from table where x is greater than that number, and now I send that string across. Remember I said R doesn't care what's in the string, and SQL only looks at the string. It doesn't know where the string came from, okay? So we can build it in R. Okay, we can sort of say, you do care what's in the string. Okay, so you will help us build it, but then we just send the string across. So we're now dynamically constructing something. So here's one of the things we can do. Get 2 quantiles, okay? I'm going to select Y from the table, and I get all the answers back, okay? But then I compute the 2 quantiles, the 10% and the 90th quantile. Okay, so I've brought all the data back. Now I've got the quantiles, and now I stick them into the string. So I say select all the rows from that table where x is greater than the first quantile and less than the second quantile. And now I can do that query in the database, but I can't do it in the database because the database doesn't know about quantiles. Okay, so I can't put this into a function in the database, but I can just bring back some of the data and then build a query again, and now I can do something clever. Okay, and I could do the whole thing in R. Again, this is only I started this by saying if I have 500 million or 250 trillion observations, you're in trouble. Okay, so one purpose of using databases for large amounts of data, then you have to be somewhat intelligent about how you mix the 2 languages if it actually matters. Okay, DBs don't have a median function, and so we can't do quantiles, we can't do medians, we can't do these things. And the reason we said earlier, it doesn't have medians and quantiles because it cannot sort. Does anyone know how to compute the median without sorting? I'll make it easy. Go on.
A long time ago, you could do some sort of count and add it up.
Exactly. So we'll make life easier. Remember we started with the ages, and I just want to get the median of the ages, and that was the first question I asked you. Well, one way to do it, you could do this in R2, but is basically I say I get age 1, age 2, age 3, age 100, or however my range is, and I get the counts. We had 3 of these, we had 102 of these, and we had 2,000 of these, and so forth. That is a summary, that is a histogram essentially of these things. For integer valued numbers, or for where we actually have where we have a fixed precision, 2 decimal places or whatever, okay? And we can basically build a large table and get the counts, and now we can actually compute the median by just holding that table around. So we can actually approximate the median in certain cases, but we can actually calculate it exactly for certain types of data. And this is a kind of good thing. I could just ask this database, give me these tables. Give me the table in R, the actual count frequency table. I can compute the median and stick it back in again. But I'm now actually got very little data coming back, and I only got as many unique observations as there are, and I can do a group by and a sum in the group by. I get this, and I can compute the medians. So it's kind of funny that some of you think they don't compute the medians because they can't in general, but they can in a lot of cases, especially if we just round to a certain number of decimal places. We can actually compute the median. And that's how we have to start being creative about doing this. What I was basically doing there was I was bringing the data back to R, getting some values in R, and then doing a second query. we can do subqueries to actually do this all in one go if we can, okay? And that is, where are we doing this, okay? So where are we? Let's just take a look at this, which is, we can do this sort of thing. Select from all the columns from the orders where the amount is greater than, now let's just go and compute the average amount from orders, and we get back a single number here, okay? This is a simple select, we get one number back, okay? One row, one column, and then it compares to this, and this parenthesis says, put this, do this first, get the answer, stick the answer in here, and then use it in the outer query, in this inner query. Okay, this is a subquery. So whenever you see these things here before the select, that's a subquery. Everyone happy? Okay, who knows about joins? Okay, up you come. So joins, these are the joins. Personally, it's the one on the bottom that we're going to use all the time. Okay, the one you can't quite see. This is too big. Okay, this is confusing. Okay, it's the inner join. Okay, but we have left joins and right joins and so forth. This is the inner join. Okay, we have the customer and order data. Okay, and this is, I'm using examples here. The way people define joins to me is hopelessly imprecise. Okay, so it's very hard to understand what they're actually doing. And then the way we define them properly is hopelessly complicated and symbolic. So what are we trying to actually do? Is basically we're going to get all of the customers who placed an order, and we're going to get the details of each of those. Okay, so you want to think about it in two different ways, which is we want, this is the customer database. Okay, we want all of the rows here to match up with the customer ID in the orders, okay? And anyone here who didn't have an order, we don't want to see them. But anyone who had multiple orders, we want to see multiple rows from this table corresponding to the customer ID over in the order table. Does that make sense? Yep. Everyone happy? We can go ahead and actually, we can run it if you want. Actually, so you can actually, so we can do this. This is the inner join on these guys, and that is our result. Okay, so we get 2 from Thomas Jefferson. He's number 3. If you want to go back, and this is where I really, really urge you to go through this. This is a tiny data set, and you can actually go through and say, what should be happening here? Okay, so this is the customer, okay, and this is the order data. This is 3. If we go back to customer 3, we see Thomas Jefferson, and lo and behold, we should have 2 rows of Thomas Jefferson. We're getting the first name, the last name, the order date, and the amount. This is the first time we've actually seen it. It's kind of a bit weird. I hate the syntax, but some people love it. Okay, we're actually saying do an inner join. You never need to say inner join, outer join, left join, right join. You can do the whole thing with select commands directly. And there's logic and there's conditions on this, but it's fine. But we're actually merging the columns from 2 different tables. Okay, the order date is coming from order, where the first and last name is coming from customer. Okay, and basically, so I hope what you're seeing, and hopefully this is clear, although it's not, I don't think. Okay, but basically what it is we're saying is they will combine, join the rows from this table and this table where we actually have a match between the key, this key and this key here. Okay, anything that doesn't have a match gets thrown away. But it's not as simple as the way people say it, which is, oh, just take the rows from here and actually match them up to here in some way that's a little bit imprecise and blah, blah, blah. We need to get 2 rows corresponding to here. So if you're thinking in R, we need to actually match this into here. That's where we don't get the first one, because we actually get to rematch this one again. So you rematch this guy where there are multiplicities into ones which are unique, and now we know which rows to pull out. So what we're actually going to do is a left join on this, or an inner join on this with this, which basically means go expand the columns in this, which correspond to the guys over here. There's another way of putting it. Not sure that helps. Okay, but that's what's actually going on. Here we have multiplicity. This is not a unique key. This is the unique key. So we actually have to find the rows here that actually correspond to the ones over here and repeat these multiple times. That's why it's so easy to do in R. Okay, is that clear? Yep. Why is it different from a right join? I will show you what's okay. I won't show you what's why a right join. So the inner join is actually going to do the same thing. It doesn't matter which direction we do it in. The left join and the right join will be asymmetric, okay? But you can just switch it round and you get the same thing. If we do the joins, let's do a left join and let's see what it actually gives it, and then we can then figure out what is the definition of this. So that was the inner join. Okay. Notice, by the way, I'll give you the hint. There are no null values here. Okay. There's no. Everybody has a name and everybody has an order amount. That means the order amounts here died. Okay. 10 and 9 were not in the database or in the table in the customer ID, so there was no person there. So the inner join basically will avoid nulls. Okay, when we're matching. Okay, if there's a null here, it will show up, okay? But not when we're actually doing the matching. If we don't do a match, we don't include those rows. Whereas the left join, okay, this is a left join, and now we get back something slightly different. So what do we get back? George Washington, we get John Adams, we get Thomas Jefferson. So we've got exactly the same database back, but it's included the rows in the customer ID that didn't have any orders. That didn't have any orders. Yes, that's the man. This gets confusing. Okay, so that's what the left join is doing. The right join would be, let's just swap those guys around and do a left join. Okay, the left join and right join are just, I don't know, there. Okay, so it's holding the nulls around. So basically, if I want to see everybody, and then I don't care whether they had an order, but I want them back present in the result, I do a left join or a right join. If I only want to see people where they have a corresponding row in each table, at least one corresponding row in each table, that's an inner join. For the most part, we do inner joins. Okay, we're actually not interested in the people who didn't satisfy that criteria. Yep.
If you were interested in the people who didn't satisfy that criteria, is there something you can do in R now that you have that result in those 2 points?
In this?
Yeah.
We can definitely look at this and say, are you a missing value in here now? We can now say what's missing in here. Yeah, does that make sense? Because these will be actually in R. I'm doing this in SQL Lite 3, so we're not seeing missing.
Okay.
We're not doing so, but it's exactly the same thing. When this comes back in R, it's just easier to type here because I'm actually not running. Okay, but because I don't need to say db get query or something. These will be missing values. I can definitely look at those missing values if I so desire. Now, if this is missing, this could be missing in this table too, but we actually have a match. So I've elected to throw away the customer IDs here. But we can't quite tell whether these values were missing in the original order table, but there was a match from the order, which is okay, so that we've lost information there. I would probably go back and do your thing, not in R with missing values here. I would actually sort of say, go find me in this table the ones which have no corresponding value. Okay, and we could actually use, does that make sense? Where we actually don't get these back, we just get these back. How would we do that? No, the having is for the group buys. It's the where command. I know it's really it's okay. So, but we could do it on a where. Now, I've mentioned this, and if you don't get this, this is fine. But this is this is the left, and then we left join on this white guy here. We can do this with, as I mentioned, with no mention of the word join here. We can just basically go in and say, do this. Literally, we can take this out of a query and put it and use exactly. We actually can do less typing, but this makes it clear what we're doing. But we're basically saying c.customer ID equals o.customer ID. That's how we're joining. That's how we're connecting the rows in the two tables. Well, we can do the same thing. We can basically say where the C.customer ID is not in the row, in the order customer ID. And we have this in Word, so we can basically say which ones aren't in that, and that would give us back the ones we didn't have an order for. And that would be an easier way of doing it, rather than getting back a lot of stuff and then trying to figure it out in R. But this is the beauty: you have two choices as to where to do things, okay? And one's easier than the other. It depends on what the task is, okay? So that's the inner join, okay? The outer join, the left join, should I say, is if we actually want to keep the nulls. There is a thing called a full join, which will actually get all the nulls from both sides of the table. And then there's a wonderful thing, which is an outer join, okay? Don't ever do that. Okay, never do that. The lights will dim, okay? The world's power will come to a complete end, okay? It'll basically do every crossover of every single row. So if you take 2 million observations here and 8 million observations here, you will get all possible combinations, and you never want that. It's just making a big mess of your data, okay? That's how you do an inner join in R, I believe. Okay, left join, that's how you do that left join. It's a little more complicated, but it's not very complicated. You basically have to go and piece the two rows together. Okay, we'll finish up in a moment. So this is the interesting thing about where do you actually compute these things, and understanding about how to reduce the data. Reducing data is key if you have a lot of data. If you're dealing with a small amount of data, just slop it back into R. Do whatever you want. Okay, do it in the database. Do a thing. Do it on the back of the calculator. You know, sort of on the back of an envelope. Do it in, you know, whatever you want. It may not be that important, but sometimes it is. But also certain things are better from a reliability point of view. What I'm about to say is not. But there is this thing. You can define user function. You can add functionality to databases. If you're on a client-server database, you have about as much chance of defining a function as owning the machine. You have to negotiate with the system administrator to install a user-defined function. And I doubt anyone would let you do it, okay? And would certainly take an awful lot of paperwork to be able to do it. But if you're in SQL Lite or you own the server yourself, hey, you're good to go. There are ways to define the function. And if you can define functions over in the database that actually minimize the data transfer coming back, this can be a really good thing. So I did this with the RSQL Lite UDF package. And what you can do is things like this, okay? You basically say, okay, let's do this. You run this command. You start saying, okay, we connect up here. By the way, just enable the extensions. Now we do this weird, wacky thing. Don't worry, okay? Okay. I take some C code, because the way you write extensions functions, I can write anything I want, as long as I know how to write in C. That's not quite true, okay? But what I basically do is say, hey, I've got a C routine that I implemented, which is a stupid example, it just computes the floor, okay, the rounding down, okay? Okay, so now I just basically say, hey, database, you have a new function called myFloor, okay? So we can extend this, and I'll show you that it's not that hard. Right? If you don't know C, it's hard, but it's not really that hard. You could mimic this, but we'll get there fast. So now what I can actually do is I can do computations in the database rather than bringing them back and doing them in R. Again, sometimes useful, especially if I'm ending up with, if I'm filtering an awful lot of rows before they're even being considered by the database, essentially, to being put back in the result, I'm saving a huge amount of time. This is good. This is the annoying. This floor says I can deal with integers, I can deal with nulls, I can deal with numbers. So it's not that hard, it's just annoying. But the nice thing you can do is this. You can write R functions, okay? You just say, hey, database, here's a function that I want you to be called, okay? I want you to call it April May. It's a stupid function, okay? Okay? You don't have regular expressions, we do. I want to do the computations there because it's going to make my life easier. So I just say, here's a database. Okay, here's a database function. Now I can actually call it. I can filter it saying, if you're not an April May, if that doesn't return true, you're not April May, so I don't want you. Okay, and so you can actually just, you can define new functions that are actually implemented in R. Okay, what's the downside of that?
You gotta bring in that data, right?
What?
You might be bringing in more data than you prefer to bring in.
In SQL Lite, we're in SQL Lite here. We can do this over in the data. If we can do this in Postgres and in Quest, we're not bringing in data because we're in the database server. Okay, so the data is local. That's the key idea here. We're not moving the data to R. Or, okay, actually we're moving R to the database. Okay, so that's good, but there is another drawback. Oh, we could probably, if I wrote the function better, we could actually, we could probably actually grab the error messages. Yeah, we could probably propagate the error messages. I just haven't done it. Now the real problem is, what's the problem with R generally? Forget the database. What's the problem with R? Slow. It's very slow. This is a function call for each cell, for each scalar value, which means when we want to vectorize this is annoying. Okay, and the database does not do this, so it's a real pain. So one of the things, again, I'll just think, one of the things I actually have a proof of concept is we can actually compile some of these functions to actually make them C code down there as fast as they can be, and then they go back into the database, and this actually works really well. Okay, but this, okay, I'm just showing you how you register a function, an R function, to actually do scalar values. That's the record functions. You can do aggregate functions too. So here's something that actually tries to compute the mean. Why do we care? This is just a silly example. We can compute the median over here in R. We get called once for every record. We put it into the right bucket. At the end of the day, we end up with a frequency table, and off we go. Okay, so you have these facilities for doing this if you actually ever want them. Okay, so there are some. These are some of the resources. These are the databases. There's your DB browser. Here are many R packages. There are a whole lot of ways you can go with SQL DF. You can in data tables. There's ways of actually integrating the SQL, hiding it or explicitly using it in R as regular top-level syntax, or by actually having you type x square bracket I and it turns it into an SQL query. So you can go in different ways, but the key thing is to actually understand what's going on under the table and where the data are being transferred and so forth. That's this. And by the way, if you the SQL for Smarties, MySQL. I wrote this. My colleague and I wrote this. If you're interested in actually playing around with databases, baseball databases is nice. If you're not interested in databases, movie database, there's lots of other databases. But this goes through a bunch of actual how to reason about SQL queries and combine across tables and go through step by step, integrating some of the computations back into R and doing plots and filtering some of the results back. And so it's an actual case study, because part of this is SQL is dry until you actually start, like any language, you go, yeah, all seemed very simple until I actually went to actually type. And then it's like, okay, but it is very simple. There's a case study for these things. Thank you. And, yep. Any questions? Any thoughts? No, you're all being chatting. Okay, I will see you. I'm going off to write some letters. I finished at 12 o'clock. That was pretty good. No. You can't, I would say you can't.